Hello everyone, welcome back to my channel. Today we are diving deeper into PID control, specifically focusing on derivative ahead PID control, or simply written as PID. Standard PID control has a critical flaw. When the reference value, for example ZD, behaves like a step input function, the derivative terms generates an excessively large actuator input. In real-world engineering, this can easily damage the hardware. We will build on the case study from our last episode. This time, we will set the road disturbance Z0 to 0, meaning the vehicle is right on a perfectly flat road. Now, imagine the vehicle is about to cross a flooded area, and we need active suspension to proactively raise the ride height by 5 centimeters. Therefore, our reference value curve ZD can be modeled as a step input with amplitude of 0.05 meters, triggering exactly at 1 second. The equation of motion remains unchanged. And inside our Simulink model, the road disturbance here, this is 0, so type constant. Double click it, change the value to 0. Okay, then the reference value, this is the step input function. So delete it and type step, double click it. The time is 1 second and the inertial value is 0. The final value is 0.05 meter. Alright. Then in the output, we route the controller output as UPID, which physically maps to the input current fed into the actuator. So delete ZD, Z and Z0. Here, connect to the output of PID control. This type U PID. Alright. Before we run it, we need to change in the model settings. Here, delete the input data structure. Delete it. Okay. Then run it. Double click the result. As you can see, the red line, this is the UPID. Obviously, if you actually pump a current spike like this into the actuator, it's going to fry instantly. But why does it draw such a massive current? Let's take a look back at the standard PID control equations. Let's return to the motion equation. The KD term, this term, here, it differentiates the arrow E, which mathematically requires taking the derivative of the reference value itself. Since our reference is a sharp step input, its derivative instantly spikes to infinity. Knowing this, it's no surprise that such an astronomical input current is generated. So, how do we fix this? Since the reference value is arbitrary changed by human command, it inherently lacks physical inertia. As I mentioned in the last episode, the physics of the derivative term is essentially acting as a damper. Instead of differentiating the unstable reference, why don't we apply the damping directly to the output result? The result here is our vehicle displacement Z. Because it represents a physical quantity with actual inertia, it can never experience an instantaneous jump. By modding our equation to this, delete the original term, minus KD times Z dot. Alright, we arrive at what we call derivative ahead PID control. Then we are going to the Simulink model and modify the derivative ahead PID control. Alright, return to the Simulink model. First, this is the traditional PID control. First, combine these terms together, create a subsystem, and rename it PID. This is the traditional PID control. And the input is the road disturbance Z0 and our reference value ZD. This is step input. Alright. Let me adjust the layout. And copy it. Create a new one. And this is our derivative ahead PID control. So I rename it as PID. Double click it. In the derivative ahead PID control, in this equation, we only need to revise this term. So here, delete the line and link to Z. Z after Z dot times KD. This is again KD. And revise it to minus. Alright. This is derivative ahead PID control subsystem. Return and then connect to the road disturbance Z0 and our reference value ZD. The output here is PID control, PID. And for the mux, let me revise the input to 2 channels. Alright, let's run it. Okay. The result is very clear. The traditional PID is the blue line, and this is infinity. And the yellow line is our derivative ahead PID control. And the current is only 0.1. So this is friendly for our actuator. And let me change the scaling to auto. So look, this is the traditional PID control. If we pump this spike to our actuator, there's no doubt that the actuator will be fried instantly. Alright, this is derivative ahead PID control. If you like it, please give me a like. Thank you. See you next time.